In this section I'm going to talk about adding, and I've come up with a little sample here that I think runs through many of the problems we could run into when we're doing an addition. So I'm going to assume the first number is 951 and the second number is 62. One of the first problems you'll run into when you attempt to do the addition here is noticing that these of course are arrays. This guy would have index 0, 1, and 2 potentially, and this guy would have index 0 and 1. This is going to be a problem because as you try to add up these columns, you're going to be looking at different indices into each array. There's an easy way around that, and that would be to just pad the smaller number to be as big as the large number with leading zeros. Mathematically, of course, that doesn't change anything for addition, but now it means that the indices for these will be the same then. So that's what we want to go for, because that would make things a little easier to work with. The other thing you'll notice is with addition, we of course want to work right to left, but that's not really a big problem. When you write your loop to visit each column of our numbers, you would just start from the end and work your way back, probably stepping down, not stepping up as we normally do. So I leave that in your hands, and of course if you flipped your array storage the other way around, then you'd have to figure out however you're doing that. I'm assuming that we're doing this where our number is stored, as I talked about in the other demos, where the most significant digit is actually the first element of the array. And if you've done something differently, you'll have to compensate for that. Okay, so now that we've got our array set up, we want to add these things by column. And something you'll need to factor in, of course, is the carry from the previous column. In the first column that we work, we won't actually have any carry, but we can denote what your carry variable would look like by maybe putting it over here and setting it up with 0, because that would be the initial state for carry. We would then sum the two numbers in the appropriate column and add on the carry. So this is going to be 1 plus 2 plus 0, so I now have my answer of 3, and I would insert that into my number, my result. Now that this is done, I can get rid of that stuff, and my carry would be reset to 0 because I've consumed it in the column. Moving on to the next column, I would add these guys up. So this is 6 plus 5 plus 0 for my carry, and this is going to give me 11. I would only take the last digit, which would be the 1, and the carry would now become 1. I would then sum up these guys. This would be 9 plus 0 plus 1. So again, I take the last digit, which would be 10, and I'd set my carry to 1 for the next round. This is one of the problems you'll have to contend with in your code, because of course I'm out of numbers now in my source digits. So if you get to the end of your looping construct and you've got no more digits to deal with, do in fact make sure you still process the carry, if it's a 1, to add that number in. Now, depending on how you've done this, you may have written your numbers or inserted your numbers or added your numbers, depending on how you've done it, to the new resultant Giganteger that you're trying to pass back. If you added the numbers in, of course we would have added the 3, the 1, the 0, and the 1, making our numbers backwards. So you'd have to reverse this and make sure that you turn it around to be the right result. If you inserted the numbers into the result, then that would be fine, because you could always insert them at the front, and that would make them come out in the correct order. When you come up with your return value, do make sure that you clear it out, otherwise you'll end up with your return value starting out with 0, and then as you insert your other numbers, the 0 will end up in the result. And that could mean we add our 1013, or if it got reversed, it would be somewhere in there, terribly at the end maybe, which would make our number 10 times bigger than it should be. So do watch out for that. So there's some things to consider, and hopefully that helps you out. In this section I'm going to talk a little bit about the subtraction component of the lab, and before we get too far away, we need to remember that subtraction is not commutative, so the order does matter. So we will always say it's the invoking object, or the left hand side, minus the right hand side. It's not really a big deal, but it is something we need to keep in mind. So like addition, I would suggest that you start off by padding your numbers with zeros, and I've come up with 3 examples here to kind of illustrate some of the problems you'll run into and some things to consider. So if we pad up the numbers to be the same length, that'll make things a little easier when we go and iterate over our arrays, because then the indices will be the same. So in the ideal case, our second number is going to be smaller than the first number, and if we process these numbers, we'll see there's no borrowing to consider, but of course we will definitely need to consider borrowing, so I've got some other examples to deal with that as well. So we're going to work from the right hand side and work to the left like we did with addition, because we need to process the more insignificant numbers of the number first, because borrowing works right to left. So we would subtract 3 from 6 in this case. We would be left with 3, and then we would subtract 0 from 5, and we'd be left with 5. And we are now out of numbers in our array, so we're done. And that is the correct answer, so we know that works. In the second example here, we're going to have to start considering borrow. So you're going to need a borrow flag involved, and it would probably start out as 0 because there is no borrowing until we start doing some work. So I'm just going to note that with a borrow flag of 0. So how borrowing would work is when we get into the situation where we process a number where the number we're subtracting is bigger than the number we're subtracting from, we would need to mark our borrow flag as 1 because that's going to propagate to the next column, and we would increase our number by 10 because we borrowed 10 from the next column. So now I've got 16 minus 9, so I'd mark my 7 and I would proceed into the next column. So how the borrowing would work in this case is as I enter that part of the loop, if I find that the borrow flag is 1, I would clear it. I would subtract 1 from this number and then carry on. So 0 from 4, 4. So this is sort of the simple case of borrowing. It does not consider propagation of borrowing, so we'll talk about that in a more complicated example over here. Okay, so in this case I'm going to start out with a borrow flag of 0 again, and I notice that in the first column I find that the number I'm subtracting is bigger than the number I'm subtracting from, so I'll mark my borrow for running into the next column and give myself an extra 10. So I am now good to go and do this, so I get my 7 and I can enter the next column. When I enter the next column, I see that the borrow flag is set, so I would clear that and reduce this number by 1. I can now proceed with the normal subtraction. The number I'm subtracting is bigger, so I'd set my borrow flag to 1 and I'd pump this guy up by 10. I'm now free to do this, so I get my 8 and I'm done. If you fall out of your main loop and see that your borrow flag is still set, it means the number was bigger on the right hand side than the left and you've got a problem. This we would throw an exception for in our code because the second number was too big. If there are more digits and the borrowing cascaded, you would keep doing this process, which will work as long as there's more digits on the top until we get to the end where the borrow may or may not stay set. So this is an example of propagation of borrow. So I'll set up my initial states. Borrow would be 0, and I'll pad out this number to be the same length as the left-hand side. So when I come to process the first column, the first number is bigger than the number I'm borrowing from, so I'll mark borrow as being 1, make this number 10, and I can do the subtraction, leaving 9. Now we're done with this column. When I enter the next column, if borrow is set, I clear it, and I make this number 1 smaller. So because it's 0, when I make this 9, in this special case, I have to make sure that I borrow. So I'm going to set the borrow flag as a 1. If I've borrowed from 0, the number is guaranteed to be 9. So my flag would be set as a 1, and this will stay for the next iteration because it's already set. So I can do my subtraction. There's no number this could be that would be a problem, but 0 from 9 leaves this as 9, and my borrow flag is still set. So when I come into the next iteration, I would clear the borrow flag because it's set, make this a 9. Because it's borrowed, I have to set the borrow flag back to 1, and I would repeat now the process. I enter this last column, the borrow flag was set, which means this has to go down by 1. It wasn't 0 this time, so I'm not propagating a borrow, and I would complete the math here, leaving that to be a 0. So when I exit this, I would need to make sure that I strip my leading zeros, if there were any, and my result then could roll back as just this component. Again, if you find that your borrow flag is set upon exit of the last iteration, then the second number, the right-hand side, was too big and you need to throw an exception, because none of the normal tests will include a right-hand side that's bigger than the left-hand side unless I'm looking for that exception. Okay, I hope that helps. Good luck. In this section, I'm going to talk a little bit about slow multiplying, which is one of the easier functions we get to write, and it does rely on a few other functions working, as we'll see as we go through it. In general, though, when we think about 4 by 3, what that really means is we're going to be having 4 groups of 3. So I view that in my mind as being 3 plus 3 plus 3 plus 3, which is 12. The reverse is also true because this is commutative, so that could be 3 groups of 4. So 4, 4, 4, if I add that up, I should get 12. So this is probably one of the simpler functions because really all we need to do is iterate n number of times, summing up the other number. So if I were to iterate 3 times, I could just iterate 4 plus 4 plus 4, and I'll get my answer. This does require that I have addition available to me, and it requires that I have subtraction available because I need to subtract 1 off of this number until it becomes 0, and I need to be able to add these numbers up. So in my code, the functions I used were add, subtract, and I wrote a function called isBigger, but you certainly could use equals to check for 0 when you're counting down. If that's the case, this becomes a simple loop. You sum up your numbers n number of times, you fall out returning the answer. This could be optimized a little bit as well. If you were to identify the smaller number between the two numbers you're multiplying, you would want to use that number as the iteration value, because this would become problematic if I had 1 million times 1. I'd certainly want to iterate 1 time, adding a million on to my result, as opposed to iterating a million times, adding 1 on to my result. I didn't put this optimization into my slow multiply, but you certainly could, and it would make you watch test code for a shorter period of time, I suppose, so there's some incentive. Yeah, so easy function. Hopefully this one doesn't give you too much trouble. In this section, I'm going to discuss fast multiply, and fast multiply requires that we do what we do in some of the other operations here. Make sure that we pad both numbers up so that they're the same length. We need to multiply in fast multiply each digit times every other digit. So this is going to come up with a loop in a loop or a quadratic looping situation. So it helps very much to make sure that they are of equal length, these two arrays. So padding zeros is the way to achieve that, and it doesn't matter which order we go through when we do the multiplying. So we don't have to go right to left in this case. It actually makes no difference. So I'm going to start at index 0 in both my arrays, and I would multiply the 0 times the 2 and the 0 times the 3, or however many digits there are in this number. Any situation where I have 0 times something I can just ignore. It's going to contribute 0 to the final answer, so zeros are nice. I can just remove them right out of the equation. When I get onto this number, I have to multiply 9 times 2 and 9 times 3. And then my looping construct would be done. So the 9 times 2, I'm going to write that in, 9 times 2, I'm going to leave that for a minute, and then I have 9 times 3, which is pretty straightforward. That would be 27. Because the 2, though, is one position over, that's really 9 times 20. And what I'm going to do to calculate this in my code is every digit that I multiply, I will pad on a number of zeros for the offset of that value in the array from the end. The 3 is at the end, so I'd add no padding, but the 2 is 1 in from the end, so I'd add a 0. And I literally view this as 9 times 2 is 18, but then I pad on the number of zeros for the number of offset between the two digits. 9 is going to have no padding, 2 would have 1 digit of padding. If these numbers were further over, of course, I would just sum all the padding zeros and add them on to the end. So really all you're ever doing is multiplying one digit by one digit and then inserting padding at the end for the offset of the position into the number from the end. I can now sum these things up. 207 is my answer, and I'm done. So obviously the more digits there are, the more complex this gets and the more times it has to iterate, but really all it is digit times digit plus offset and then sum up for each step, excluding zeros. It's actually fairly straightforward. You just have to watch and make sure that your math is correct for calculating your offsets and summing them up. This works very, very quickly in relation to slow multiply, and I will be able to multiply gigantic numbers, and I should get results relatively quickly in the test code. So I would write this function last because it does require that we have summing available to us, and it's a little more complex in terms of the quadratic loop and the fact that you need to be able to calculate your position relative to the end of the number. 2 is one step away, for example, so I'd be adding in one digit. You need to be able to do this for both digits, and of course it has to reliably work over very large numbers. So I would think about it a little bit before you code, but again, still not super complex, and you'll be surprised and pleased how quickly it works. So good luck with that one.